In this video we will be covering how the scattered alpha particle is going to be affected by the scattering angle, the incident alpha particles kinetic energy, and total charge of nucleus. First we will consider how the scattering angle is going to affect the number of scattered alpha particles, and from this expression we can see clearly that the number of alpha particles which are scattered is inversely proportional to the fourth power of sine of theta by 2, which means that if you are having an angle which is smaller, your sine value will be smaller, and your denominator will be smaller, which will leads to you more number of scattered alpha particles, which means that if you are having a scattering angle which is smaller, you will be having more number of alpha particles which are scattered. And if you increase this theta, then we will be having your denominator in your denominator we will be having maximum value, or your value will be increased, and the number of scattered alpha particles will be minimum. For example, in this case, when you are having alpha particles which are coming and hitting on this nucleus and coming back in the same direction, which are the back scattered alpha particles, in that case you will be having an angle of 180 degree. Okay. Now if you substitute this 180 degree in your equation, then you will be having sine of 90, which is the maximum value of the sine, and which will leads you the number of alpha particles scattered at that particular angle is will be minimum, because when you are substituting this 180, then you will be having in your denominator you will be having maximum, and the n of theta value will be minimum. So which means that the number of backscattered alpha particles will be very, very small, and the number of alpha particles which are scattered with the lower angle will be larger. So that's how the scattering angle affects on the number of alpha particles which are scattered. And now we will consider how the kinetic energy of the incident alpha particle is going to affect the number of alpha particles which are scattered. So let's say this is your nucleus, and now we will consider the alpha particles which are coming or approaching this nucleus like this. So let's say like this, it's going like this. Okay. Now we'll take another alpha particles which are coming in the same way, but which is having different kinetic energy, will produce its angle different. So it will be like this. Okay. How this is going to happen? That is our question. So this is having the first case is having an angle of theta, and the second one is having an angle of first one is angle of theta, and second one is having an angle of theta dash. Okay. So in this particular case we will be having a kinetic energy Ke1 and Ke2. So the yellow one, which are the alpha particles which are having kinetic energy of Ke2, and the blue one is having the alpha particles which are having kinetic energy of Ke1. Now if you in this particular case I can say Ke1 is larger than Ke2. So when your alpha particles are approaching this nucleus, the nucleus is having an impact on this alpha particle because of this electric field produced by the charge, this positive charge. So there will be a force which is QE that will be interacting with these incoming alpha particles. So if this incoming alpha particle is having more kinetic energy, that alpha particles will be affected less as compared to the alpha particles which are having low kinetic energy. So when this incident alpha particles having lower kinetic energy, it will be affected, or impact of on this those alpha particles will be large. It is like when you are having a very high speed motor vehicle or car, then you cannot have that much impact on that particular vehicle. If you are moving it very slowly, then you can easily control it, or you can have any impact on that kind of situation. Okay, so when you are having kinetic energy which is larger, then the effect or impact of nucleus on that particular alpha particles will be smaller. So how this is, for example, if you are having a detector here at this angle of theta, okay, so you will be having n number of alpha particles which are scattered at an angle of theta, and if you increase then the alpha particles kinetic energy, then more number of alpha particles shifted into this angle, into theta dash, and your number of alpha particles which are scattered in theta angle, scattering angle theta, will be decreased. Okay, so if you are increasing kinetic energy, the number of alpha particles which are scattered in a particular angle will be decreased. If you are decreasing kinetic energy, and your number of alpha particles will be increased for that particular angle. And third one is how these nuclear charge affect on this scattering. So in that case, suppose this is the nucleus, and if you are having a charge which is let's say charge is q, let's take another one also for the same case, and this is having a charge q, this is having a charge q, and this is having a charge q plus let's say dq. Okay, so this one is having more charge as compared to this case. Now if you are having alpha particles which are coming and approaching this nucleus and scattered, okay, so this is your angle theta, and you are having a detector is at angle theta. Okay, this is the angle theta, so your angle, this detector is also at this angle theta. And in the same scenario, if you consider in the second case, okay, in that case you will be having with the same angle theta here. So what will happen? You will be having more alpha particles like this, more alpha particles which are undeflected or which are deflected very with very low scattering angle, very small scattering angle. So when you are having when you increase, in this case for example you are having a field like this, but when you are having more charge you will be having more field here. Okay, so more number of alpha particles will be having impact, and they can be scattered into that particular angle when you are increasing your charge. So when you are increasing your charge of the nuclear charge, or when you are changing your nucleus from a lower nucleus of having lower nuclear charge to a nucleus having higher nuclear charge, then more number of alpha particles get impacted and can be scattered into a particular angle. So the number of alpha particles will increase when you are having large value of nuclear charge. So in the size comparison, we have one size comparison here. Let's say for the case of hydrogen atom, we will be having atomic size which is equal to 50,000 times size of the nucleus, which means that if you consider 50,000 number of nucleus arranged in like this in a series way, 50,000 number of nucleus, then you will be having a size of atom. Okay, so if you consider that with this system, that is solar system equal to 6,000 sun size of the sun. So if you arrange 6,000 sun, you will get the solar system. If you arrange 50,000 of nucleus, then you will get atomic size. So it is the size of nucleus is that much very small. So it is in the order of 10 raised to minus 15, which is the femtometer, or in femto range. So which means that it will be 0.000 times 10 to the power 14, that is 14 0, 10 to the power 15, that is 14 0 and 1, that is the size of your nucleus.